Welcome to EELE 261 Introduction to Logic Circuits. My name is LaMeres and I will be your instructor for this fully online course during the summer of 2022. In this video, what I'd like to do is introduce the course and what we're going to be covering in terms of why it's important and where you go from here. And then I'd like to introduce myself as the voice that you'll hear in all the videos and the hands that you'll see drawing and everything. And then finally, I'd like to go through the course logistics so that you know at the end of this video exactly what to do. So where the information is located, what your activities are, and what is graded. All right, so let's get started. This course is the first in a series of courses where you learn about what a computer is. So a computer is a device that operates on information that is stored and manipulated in what we call binary, or ones and zeros. You probably have heard of a computer operating on binary. All a one and a zero is essentially a true or a false or an on or an off, and that's what we call logic, okay? And so a logic circuit is something that only operates on inputs that can take on a true or a false or a one or a zero and output a value that is either a one or a zero or a true and a false. So that's what a logic circuit is. And it turns out that logic circuits are the building blocks of all computer hardware because a computer in itself is a digital device or a logic device. Now, a computer is a collection of hardware and software, and the hardware of a computer is designed to execute a predetermined number of instructions. So these are already built into the computer hardware. We provide what instructions are going to be executed and in a particular order to the computer hardware in order to accomplish a task. And so a computer is a collection of hardware and software where the software is nothing more than the list of instructions to execute and in what order. Now, computer hardware takes many forms. It can be laptops and desktops. It can be servers. It comes in PC and Macs. It comes in, iPhones and Androids. And that's fine, but it's all the same stuff. It's all ones and zeros being acted upon by logic circuits. So in this class, what we do is we start at the very beginning. We start looking at the most basic logic circuits there are, which are called logic gates. And these are simple things like if you invert the input. So if it's a 1, make the output a 0. If the input's a 0, make the output a 1. And we build up more and more complex circuits to the point that we can then take on more advanced classes where we put the circuits together and actually build a computer. But we are in this class looking at the low-level hardware that sits beneath the hood of an actual digital computer. We are not looking at the software that is used to tell the computer what to execute. Okay, so that's what this class is about. It's like I say, you won't know exactly what a computer does at the end of this class, but you'll have the start so that you can take on the follow-on classes that do teach you what a computer actually looks like underneath. Okay, so the topics that we cover in this course to learn about computer hardware consist of 7 modules, and the modules represent an individual chapter in the textbook, but we don't call them a chapter in the course, we call it a module because it's both a chapter in the textbook, an associated set of videos, an associated set of homework assignments, and an associated set of laboratories. So all together we call it a module. And we cover 7 modules or corresponding to the first 7 chapters in the textbook. So we start off with just a really short module, just kind of get used to this notion of what is a digital signal. And we do that by contrasting it to an analog signal, which we might be more familiar with. Then we move into number systems, and we talked about how a computer operates on ones and zeros. So in order to understand how to build circuits that manipulate ones and zeros, we need to understand how you represent information with ones and zeros. And so we learn about how to convert a decimal number into its binary equivalent, and we learn how to do binary addition and binary subtraction, and learn how to represent binary numbers in different codes to represent positive and negative numbers, and in addition to using other number system bases in order to represent large numbers of ones and zeros. Once we get that, we turn to module 3, which is where we actually start looking at the most basic, what we call gates, or the most basic digital logic circuits that we have. And we look at these gates at the circuit level. So we actually realize that even though the inputs and outputs are ones and zeros, They are circuits. They need power, they need ground, these are parts that we can buy from the stock room. We're actually going to put these parts down on a breadboard and we'll wire them up and we'll look at the inputs and the outputs and see how they operate. Once we have that covered, then we turn to Module 4, which is where we actually start learning how to design what we call combinational logic. So we start taking a description of a circuit and saying for these combinations of ones and zeros, the output should be ones for these and zeros for those. And then we learn how to actually synthesize or create a logic circuit that can accomplish what we wanted. And we call it combinational logic design because combinational means the output of the circuit is based solely on the instantaneous input of the circuit. Okay, so there's no storage in it. It's essentially a left or right circuit. Then what we do is we move into Module 5, which is where now that we know how to design a logic circuit, we kind of take a different direction and we start learning about a hardware description language. So it turns out that while we learn about how to design logic circuits on pen and paper and we actually can breadboard them and wire them, logic circuits get really big really fast. And so it becomes impractical to be able to model a modern digital system on paper using schematics. So we've invented this thing called a hardware description language, which is a programming language that allows us to describe the functionality of a logic circuit. And that's really cool because we can describe it using text, meaning that we can describe very large systems using just alphanumeric characters. In addition to, since we're describing the functionality on a computer, we can actually perform simulations of the computer or of the description in order to verify that it's accurate. And then once we have an accurate description of what we want, we can run it through another software tool, which is called the synthesizer. And the synthesizer will actually create the logic gate schematic for us. So it'll actually pump out the final schematic that we could then build with our breadboard, or in turn, actually put it onto what we'll learn about is called a programmable logic device. So that's one of the parts that you have in your lab kit. And so this allows us to essentially design logic circuits by typing at a keyboard, which is how you'll do it in industry. But we had to get to Module 5 in order to actually even know what a logic circuit was and then how to actually create something. In Module 6, we get a little bit of practice designing very common combinational logic circuits, which we call MSI logic. It just stands for medium scale logic. It's just medium just means a little bit bigger than a very simple logic circuit. And so we go through a series of learning about various MSI logic circuits, and then we model them in our HDL or our hardware description language, and then we actually implement them or download them onto a programmable logic device and test them. And the V in Module 5, I always say HDL, but the V is a particular language. So it's VHDL. It's one of the two logic description languages that are most common in the world right now. And then we finally wrap up the course with Module 7. And this is on sequential logic. So this sequential logic refers to a circuit that has some elements of storage to it. And so we're not only going to have combinational logic circuits, but we're going to have devices that can store ones and zeros. And what this allows us to do is make a more intelligent circuit because we can base the outputs of the circuit based on current inputs and also past values of inputs. And we culminate the class with this very powerful logic circuit, which is called a finite state machine. And we'll actually build that in hardware. Okay, so before we start looking at the course logistics, let me give you a quick background on myself so you know who I am and who the voice is in all the videos. So, again, my name is Brock LaMeres. I'm a professor of electrical and computer engineering at Montana State University. I've been a professor for 16 years now, and before becoming a professor, I was a hardware design engineer for Hewlett-Packard. At Hewlett-Packard, I designed electronic test equipment, and I was responsible for the digital part of that. So I did logic circuit design using VHDL and the other hardware description language as a practicing engineer before becoming a professor. I got my bachelor's degree from Montana State University back in '98, and then while working for Hewlett-Packard, I went and got my master's degree and PhD from the University of Colorado, which Hewlett-Packard happily paid for. And so I was able to work full-time while I got those degrees. And then back in 2006, an opportunity opened up to come to MSU, and I jumped on it. And so at MSU, what I do is I teach courses in digital logic and what we call embedded systems, which is kind of like a little computer, well, basically computers. but very small computers that are embedded in all sorts of electronic devices. And then on my research side, what I'm looking at is how to exploit reprogrammable hardware in order to build novel circuits. And one of the things that we've discovered is that we can basically use the reprogrammable nature of these programmable logic devices, such as what's in your lab kit, in order to restore a hardware circuit to its original state. And we actually found an application for space computers where we could build this particular architecture, and when you put a computer in space, it crashes because radiation hits it and flips the ones to zeros and zeros to ones. And we found a way that we could build this particular architecture and actually get the computer to automatically recover. So not just reset itself, but actually restore its hardware that could have been faulted. And this got the attention of NASA about 12, 14 years ago, and they started funding demonstrations of this particular computer. And we call the computer RADPC. And so what I've been doing for many years, and I'll kind of start at the bottom, sorry to make you sick here, is demonstrating this computer on a variety of different flight vehicles. So we've built this thing up and we got approved to NASA that it works. So we've flown it on sounding rockets, which are essentially missiles that just go straight up and straight down. You can see here some pictures of what a sounding rocket might look like. That's about how big it is. It's a missile. Here's me and my team down there in New Mexico. Here's what this computer experiment might look like. It's very small, size of a Rubik's Cube, but you bolt it on there and you fly it and you test how good your computer recovers from radiation strikes. We've done a couple of those sounding rockets. We did another one out of Wallops Flight Facility in addition to New Mexico. Here I am with a student that's showing kind of the size of the second payload that we did. Then we got an opportunity to actually go to the International Space Station in 2017. And so you can see this little box right here. It's floating in the air on the space station about to get installed by an astronaut. And here's kind of the box on our bench right here. And all it's doing is just trying to test the computer in a harsher environment. And then we've had the opportunity to put 2 small satellites into orbit. So they're called small satellites because they're like the size of a loaf of bread. And so you can see this satellite being pushed out of the International Space Station. And these 2 satellites are still actually in orbit right now. We've done balloon flights. So these are high altitude balloons. So this is like the size of a skyscraper style balloon. You can see here's our computer again. Every time we do one of these flights, it's a more mature version of the computer, and we're testing another part of the system that we've made radiation tolerant. And so we've done balloon flights. Here's another satellite getting kicked out of the space station. So it's just been a long career of building and flying these space payloads that are demonstrating this particular computer. And actually right now, like within the last 2 months, we've put 2 more on the International Space Station. And this is what it looks like. You can see here's our little box right here being plugged in on a ground station right there. And there's 2 of these on the International Space Station as I'm speaking right now. And then 2 years ago, we got the big shot. We got an opportunity to go to the surface of the moon. And so we're actually building up this computer, and we're going to go on an unmanned lunar lander, which is scheduled to launch in 2024. And it's actually going to carry this computer to the moon and land, and we're going to get information on how well our computer operates en route to and on the surface of the moon. So as I teach this course, this is not just something that I randomly was assigned. I mean, this is my area of passion, my area of interest. I've done logic circuit design as an engineer for Hewlett Packard. I do research on logic circuits for NASA. I study how to effectively teach logic circuits, and then I practice teaching. I actually am a teacher that has taught this material for 16 years at Montana State University and a couple years at University of Colorado. So now we're ready to actually look at the course logistics. Okay, so it all starts with our course management system, which is called Brightspace. So you go out to ecat.montana.edu. I'll scroll down here. ecat.montana.edu, and it'll take you to the login page. And then you log in with your net ID and password. And in the syllabus, it tells you some information on who to contact if you get locked out of your password or you forget your password. And so as you come down here, you'll come over to the right side and you'll start seeing a widget over here that shows the courses that you're in. You'll also see announcements that sit over here, and so you'll see announcements that pop up from the various courses. But what you should always do is go to the course itself And then from there, you can look at the specific announcements for that course. So if I come over here, I'm going to click on Intro to Logic Circuits. If you're only taking one class this summer, you'll only see one. And what you start with is the first announcement. So it always starts on the announcement tools. And you'll see basically a welcome message. And it talks about what we're going to look at this week and what assignments are going to be due, when they're due. And I'll have one of these that comes available. I'll post one of these every Sunday just to give you a quick refresher on what we're going to do for the week and when things are due. This is nothing more than just a repeat of what's in the syllabus, but I just put it in there just so that you get some sort of pop-up every Sunday. Okay, and so you have these announcements that'll come up, and this one basically says go to the course content pages and take a look at what to do. So you're sitting there going, okay, where do I go? Well, you go up to content. So I have everything linked in the content section of the course, and what you'll notice here is you have course information and syllabus, and then you have a page for all the 7 modules that we're going to cover. Then you have a final exam, okay? And so each of these is a page. So if I click on course information and syllabus, you'll come in here and you'll actually see some information about the course. So you have your course syllabus right here. You've got the course overview video that you're watching right now. And then there's actually a homework assignment on the course overview. So you can get your first point in the course by looking at this. And it's basically just going to ask questions like when are the deadlines and who's the TA. Here's my contact information. I have a WebEx room that we can use to do video calls. And email is really the best form of communication because I always have my phone with me, so I can usually reply pretty quickly. If it's a more complex thing, I'll just say I'll get back to you and wait till I get to a computer. And then Connor. Connor is your man, okay? Connor is the teaching assistant for this class, and he is on call all the time. So he is here to help, and he's going to be the one that grades. He's going to be the one that handles all your help questions. If there's anything weird that Connor can't answer just due to like a technical difficulty or a grading question, all 3 of us will work together and get it resolved. But he also has a WebEx room, and so we don't have set office hours because everybody's so different and everybody's so asynchronous these days that you can essentially work whenever you want. But if you ever need to get a hold of Connor, just email him and set up a time to call on his WebEx room, and you're off and running. Since email is such an important part of this class and such an important part of being an engineer, I actually have a little extra credit opportunity where you can read this professional email etiquette guide and get some extra credit points just by emailing me. Okay, so you can get a 2% bump right out of the gate. Just extra credit for being professional when you email. It's also something you need to do. You need to become more professional at email or before you become a practicing engineer. This course has material that is required. First one is a computer with high-speed internet running Windows. Why is it important? It's because our design software doesn't support Macs. So if you have a Mac, I'm sorry, you cannot run the software and you shouldn't take this course. Now, if you have a Mac and you're in college, more than likely you have access to a Windows machine because all engineering software runs on Windows machines now. They don't run on Macs. Some of them do. It gives you this false sense of security that maybe a Mac will work. They don't. Macs don't work for engineering. Just get rid of it and get a Windows machine. You can dual boot your Mac. Go for it. You're just going to spend twice as much time doing assignments than everybody else who has a Windows machine. So go to your campus labs if you need a Windows machine. Otherwise, you're screwed. You need a textbook. The textbook was written by me. Okay, this textbook was written after I had redesigned this course and also the follow-on course. So the material of the course was in existence and I was using it and I had debugged it and then I went back and I wrote the textbook. So this textbook is identical to what we're going to cover. We're going to go from page 1 all the way through the last page in chapter 7. Okay. If you're going to buy it, the bookstore is more expensive. I don't even tell the bookstore to carry it anymore because it's too expensive. Amazon's the best place. If you click on this link right here, this is the best place to go get it. You can come right here. Boom. It's whatever. It's only $70. You can get an ebook off and running. And then we have portable logic kit. Okay, a digital logic portable lab kit. This is critical. This is how you're going to do all the labs. Okay, you can do the labs from anywhere as long as you have a Windows machine and the kit. Okay, you're going to demo your labs by just taking pictures and videos and screenshots, but you are going to do a lot of labs in this class. That's where all the learning happens. Okay, so you need to get this kit. If you're in Bozeman, you should go see Deb in the ECE office and pick up your kit. If you're out of town, you need to email me and Deb, and I've already sent a few emails on this, so we can ship you your kit. You need this kit the first week, okay? I need just this kit to be there because you can fall behind really quickly if you don't have it. You need a camera capable of taking short videos for lab demos. That's just your smartphone. You're gonna basically build a circuit. You're gonna take a small video of it working. You can usually demo these things in 5 to 10 seconds and upload the video to the actual website in order to get graded. Okay, and that's kind of the course overview. Let's take a look at the syllabus because this has a lot of information in terms of like specific schedule. Okay, so we've already talked about the description. Everything we do in the class is to meet a learning outcome. So it's like we're not just doing stuff because it's fun. We're doing stuff to learn a specific task that is of value to industry. You already talked about me and Connor. This class starts on May 16th and it runs till August 5th. It's a fully online class, and that's it. Let's see. Course website, ecat.montana.edu. Anytime you need us, just email us and we'll set something up. The grading distribution is essentially 25% is homework, 45% is labs, that's a big dog. And then we have end of module quizzes worth 200 points or 20%, and then your final exam is worth 10%. I grade straight, so 90% is an A, not an A minus. I don't believe in A's, A minuses. I don't believe in minuses and pluses because there's no A plus. Okay, and so I just grade straight. Academic policies don't cheat. What cheating means in today's world is turning in somebody else's assignment or copying somebody else's assignment. What is not cheating is collaborating together on problems. Okay, every engineering problem will be solved by a group, and that's perfectly fine when you work these problems. We encourage you to work together. It's just that you have to turn in your own work. So if you guys are working on a program together, just make sure you're both typing it out and you're both doing your own schematic drawings and you're both building your own circuit. Okay. Course components, you are going to have the ability to read the textbook. You can read the textbook and not watch any videos if you want. That's fine. You can also watch videos. I have instructional videos for every section in the textbook, and they should be the same information, reading in the videos. So some people find that the videos are enough and they don't read. Some people don't like the videos. They read and they don't watch videos. Either is fine. We're going to have homework that is in the form of multiple choice quizzes in Brightspace, or we'll also do some simulations. Okay, so you can do simulations of logic circuits. You can take screenshots of the waveforms and you can upload your source code in your waveforms to a folder and get graded that way. We're also going to have lab assignments, which are conducted with our portable lab kit and demonstrated with short videos and screenshots and pictures. And then at the end of every module, we're going to have an end of module quiz. The difference between a multiple choice homework and a end of module quiz, they're both multiple choice forms. It's just that homework, you can open up the quiz. It's a quiz tool, right? You open up the quiz, you can work on it, you can save it, come back later. It's only due on the deadline. And once it goes away, it's gone. An end of module quiz is timed. That means that when you hit go, a timer starts and you have 30 to 90 minutes to complete the quiz. And if you don't get done, it goes away and you're done. It takes whatever you answered and gives you a grade. So you got to make sure that if you do an end of module quiz, you got to make sure you have enough time to actually execute it. Because even if you start it and you log out of Brightspace, the timer will still go and expire. Okay, so that's the big difference. End of module quizzes represent kind of like mini exams. So we'll have like 7 mini exams just to kind of give you like a timed assessment of what you learned. And then there'll be a final exam, and this is going to be a honkin' multiple choice quiz, 3 hours long, comprehensive. Okay, this is a very important document. This is the schedule. Okay, so every week is broken down into what module we're covering, what section we are going to be doing, and what assignment. Okay, notice that you have homework, lab, quizzes, and exam for points, and all the point values are over here. Not every assignment is worth the same amount of points. Some of these really simple multiple choice homeworks are worth 1 point. Okay, that's of the course, we're gonna have 1,000 points possible. So that means this isn't even worth 1% of the course. It's 0.1%. But once you do a lab, that's 20 points. That's worth 2% of your grade. And this quiz is worth 1% of the grade. Okay, so you can tell that not every graded activity is worth the same amount, and it shows that labs are the most important. Okay, especially when you get down to like the bigger labs where you might have something that's worth, this lab's worth 5% of your grade, so 50 points. As you work through these, you'll notice that every section has a homework, and then after a couple sections, you do a lab. All right. at the end of each module, you have an end of module quiz. The way that the deadlines work are as follows. They're due on Wednesday at noon, all right? So when you start the course on Monday the 16th, you're going to have a few very simple assignments, including a lab that is due the Wednesday of the first week. I want this due the first week because this class goes really quick. And if you don't have that lab kit and you're not able to get the software running for that lab kit by the first Wednesday, you're going to fall behind because on the second week, we're already banging and we already have a lab like every single week, if not two, okay? So during the first week, we're going to cover Module 1 and they're due on the first Wednesday. And then we get into the flow where Module 2 has homeworks, a lab, and a quiz, and it's due the following Wednesday. And that's going to be the flow for the rest of the semester. In week 2, we cover Module 3. All the assignments are due the following Wednesday at noon. Week 3, we start Module 4, a portion of it. All the assignments are due the following Wednesday at noon. Week 4, all the assignments are due the following Wednesday at noon. Everything's due the following Wednesday at noon. So all the deadlines in this course are due Wednesday at noon. And you can walk through every single assignment that we're going to do throughout the course. You can see all the lab assignments and finally get to the comprehensive exam. Everything adds up to be 1,000 points. So this is your go-to in terms of trying to figure out what assignment is worth what, when is it due, and when are you working on it, okay? So that is the syllabus. Let's take a look at what a normal content might look like. So if I come in here, let's just go to, let's go Module 2. So I come in here and this is what a particular module content looks like, content page. You have your learning outcomes of what we're going to learn when we go through this, and then you have your activities. Every section of the book has a section to read, and then it's got a YouTube video of me talking about it. Sometimes there's more than one YouTube video. So for example, section 2.2 actually has 3 videos. I tried not to make each video too long, but you watch these videos and then you're going to do a homework. So for example, I come into here and I click on this and it brings up a YouTube page and it's going to start making noise. Bear with me.
I can turn anyone into a beach bum.
If you want to watch an ad, go for it.
Start looking at number system.
And so here's like an example video. I'm sitting here writing on a piece of paper. So it's just like I'm in a class with you writing on a board. So that's the type of stuff that you'll see when you walk through these videos, okay? Then let's take a look at a multiple choice problem. So I click on this. It comes up. The view is a little bit different because I'm the instructor, but this is what it's going to ask. It's like, you really sure you want to start? I say, yep, I want to start. Come in here, and here we go. What is the radix of a binary number system? If you don't know what a radix is, that means you didn't watch the video or you didn't read the book, okay? What is the radix of hexadecimal? If you don't know what hexadecimal is, that means you didn't read the book or watch the video. And that's kind of the simple part of it, okay? Then you come down here and you submit the quiz, and then immediately upon submission, it'll give you your grade and it'll put the grade in the grade book. You only get to submit it once, so you can enter your points or enter your answers, save it, make sure to save it, and then when you're ready to go ahead and submit it. You just got to make sure that you submit it before the deadline, okay? So that's how most homeworks are going to be. Some of the homeworks, though, will actually have, they'll actually be like simulations. So for example, if I come back to activities, I can come down and I can say, okay, here's module 5. You're going to have some simulations in here. So like, for example, this one right here, you'll actually have, excuse me, didn't mean to click on that. You'll actually click on this and you'll get a web page that says you're going to do a simulation of a logic circuit. And it has you install some software, you implement this particular input and output configuration of the circuit, and then your homework that you upload will look like this. It'll be a waveform in addition to the source files that you actually type out. So those are going to be some of your homeworks. The last part of this is, what does a lab look like? Okay, so let's go back and let's take a look at a particular lab. So I'm going to come down here, lab 5.1. All the labs are in a single document, and they're basically every lab for the whole semester in a single PDF. And so, and this one, I update this from time to time, but it's always just a single PDF. Let's take a look down. Here is like an example of what a circuit might look like. Sorry to make you sick here. Let me get back to like a module 3. Hang on. Don't get car sick. I'm just trying to get to one. I want to show you a circuit. Here's like an example of, here's a breadboard, and then here's some logic circuits that you put down. And then what we do is we use this device called analog discovery to actually provide power to your breadboard. And so let me show you that just so you know what that is. This thing right here is the analog discovery. It provides power to your breadboard. It can drive in ones and zeros as inputs, and it can look at the outputs to see if they're ones and zeros. So this is a very powerful tool, and this is how we do everything with the lab. And then later on, you'll actually use another device, which is in your lab kit, which is called a programmable logic device, or an FPGA. And that's where we can write VHDL, simulate it, make sure it works, and then we can actually download it to the programmable logic device and actually test it. Okay? And that is it. Okay, so that is the course. So at this moment in time, you should be able to come back to the course, and you should be able to begin. So you know where the information is. You can look at the syllabus to know what is going to be worked on that week, how many points it's worth, what are the activities you need to do in terms of reading and watching videos, and then what type of homework you're going to have. Is it a multiple choice quiz, or is it going to be a simulation? And then you know the deadline, and then you're going to have a lab activity, and then you do the lab activity, you upload it into the folder that's linked on each of these content pages, and you just repeat that for 6 weeks, and then all of a sudden you know a bunch of information. You do it for 12 weeks, and then you take the final, and you're done. Okay? All right, that is the course. At this point, you're ready to begin. So good luck this summer. Keep in contact with us. We're here teaching this live. I mean, we're not just going to turn off our computers now and grade in August. We're here waiting to help you, and I look forward to working with you. So good luck.